confirms what I know. I guess those aha, oh no kind of thing. You know, what was it? What's new information that you're like, aha? And what was something that you're like,
I had several, but
Yeah.
I shouldn't, I shouldn't jump in. You all jump in, but I'll jump in with one thing.
Okay.
With one thing that really struck me that I knew already that I needed to hear again. That sometimes when students are displaying, shall we say, or exhibiting problems with the skills that we know we've practiced them on and we know they ought to know, that very often that relates back to a lack of conceptual knowledge to which the skill is related. I mean, those two, while we can separate them and think about them, we can't really separate them if we expect to develop math proficient kids.
and the writers of the standards have actually said to us, concepts come first. So that
Concepts
tells us how to
first.
sequence our unit. The conceptual expectations lead to the procedural expectations, which lead to the applications, because we need them all. So what level are we getting to? Well, if we're getting to the application level, we need it all. And what's interesting is the standards were built where some grade levels introduce the concept, but then the next grade level does the procedure. The sixth grade introduces the concept of integers, but you don't learn the procedures of integers until seventh grade, and you apply them in real world problems. So you add, subtract, multiply, divide integers in real world problems in seventh grade, but you learn the concept in sixth grade. Well, if they don't have the concept from sixth grade, you ain't adding, subtracting well, right?
So not yours, but the idea is put all this into one lesson, or
Well, I think a lesson is, we have a new definition of a lesson.
Right.
A lesson is a multi-day experience. It's however many days it takes to get the job done. And a lesson could be encompassing one standard, or it could be encompassing multiple standards, depending on how we chunk it together.
You need to integrate it, so how does that go into the integrated curriculum?
When we think about an integrated curriculum, I think we're looking at, there's layers of integration too.
Right.
An integrated curriculum could be that the course contains algebra, geometry, and stats. Or it could be that the unit integrates algebra, geometry, and stats. And I think the projects that we do in an integrated curriculum, I think are where we see the integration of the algebra, geometry, and stats. It may be a project where we integrate two of the three. It may be a project where we integrate all three, areas. But the thing is, they're starting to see the connection between them. The real difference with integrated is that integrated is much more about the progression of the functions. So you learn linear functions in 8th grade, linear and exponential in Math 1, linear, exponential, and quadratic in Math 2, linear, exponential, quadratic, trigonometric, polynomial, rational, logarithmic, Math 3. So there's that, you have everything is fair game that I mentioned in Math 3. You don't forget the other ones. They want them to see the connection between them. But they apply all those in geometry. They apply them in, so trigonometry is really geometry. That's in a lot of the expectations. But it's also functions in trigonometry. So there's a merger of those. So they're seeing that Math 3, I remember when I was in school, I took Algebra 2 Trig, which was really integrated Math 3, sort of. It's just that we didn't, that's really what it is. There's a lot more proof in geometry, but it's transformation geometry instead of theoretical. So it's a lot more practical proof, which makes sense though, because we're in the 21st century. So in the 21st century, I have tools that I can flip and slide and turn to prove that there's congruent shapes or there's similar shapes. Why would I do a theoretical proof when I could do a practical proof? What would you rather see as a human? I think I'd rather see the practical proof done right in front of me than the theoretical proof. But we also connect it to the theory, because there are some things we're just not sure we can prove. But transformational geometry can be done. So that's where it's changed a lot. The algebra has changed from the historic to the to the Common Core version, where we're seeing 8th grade is really getting the first 1/3 of what Algebra 1 was. And now Math 1 picks up from there and does the other 2/3. And takes on a little bit of Algebra 2, I mean, that's, and then Math 2 kind of has some algebra 2, some geometry. I mean, it's all, but we're seeing a lot more of the stats. The stats is been beefed up, and that's important because the workforce and colleges all said they don't know how to use data to make decisions. We didn't know how to use data to make, we don't have time to use data to make decisions, that's part of our challenge, but people didn't know how. So the stats being beefed up, starting in high school, and that is definitely gonna get them better prepared for college and universities, so that's one of the big changes.
What could be more real world?
Than stats, I know,
All of the
yeah.
applications,
Yeah. Well, and I think what's interesting is, I learned this at the model curriculum team, so I did not know this, but history of math 101, geometry came first. Because geometry and measurement were the first systems we started to use because we were trying to make sense of our world through shape and through measurement units. Then came algebra to make sense of geometry. So we want to use geometry to make sense of algebra and algebra to make sense of geometry. The integrated makes sense now that we know that. And I'm thinking, that's so duh. Like how, it does make sense if we think about, math and how it evolved. It's just that nobody really thinks back to it. So we were trying to teach algebra, not connecting it to geometry, and a lot of people don't see the connection. In fact, a lot of teachers will come up and say, I was good at algebra, but I wasn't good at geometry, or I was good at geometry, but I wasn't good at algebra. And they're connected. And they're not using one to help them understand the other. So the integrated forces that. A good teacher in math, in algebra 1 and geometry and in math algebra 2 will do that. But they have to make the time to do that, where it's in the design structure for math 1, math 2, math 3. So there were some teachers who were definitely making those connections. I don't want to say that teachers weren't doing that, but they didn't necessarily have the time to do that either. Where now it's in the design structure, they will have the time because it's planned out. It's required. So that's what we see. It's the projects, the statistical applications, the use of graphing and geometry in graphing. That's where we're seeing that interconnectedness. And I'm coming from a background where I didn't teach high school math. And I'm learning so much about it now because I learned high school procedurally. I think we all did. I'm relearning so much. And it's fascinating to me, like, oh God, I didn't learn that way. Or no wonder I lost it.
Yes.
I got a 5 on the AP Calc exam. You think I know all that now? No. But I did have it, so why don't I still have it? Because it was taught procedurally. The things that we lose are the things we only learn how to do. It sticks with you if you learn the concept.
How is the AP gonna fit in with all this?
AP would be that 4th level course for some kids. But the 4th level course doesn't have to be AP. So it's that, there's a lot of options. What the legislature is talking about is the possibility of requiring 4 years of math at the high school level, but not requiring 4 years of credit, which is interesting. Because the whole idea of credit recovery, that some kids would never be able to graduate if they were required. So you have to be in a 4th year course. It could be an applied course where you're seeing career and tech education type courses that utilize math, cite which math standards they utilize, and saying this is an application of math, so therefore we are a course that would qualify for that 4th year
Like
requirement.
drafting.
Drafting, yeah, that's one. I mean, my office is actually in a CTE building, and I said, I would love to chat with those folks sometime and say, okay, which math standards are you, they don't even know that they're doing them. But it would be a fun conversation, because if we walked through and said, they do it.
It's
Something
there,
that-
yes.
It is there.
Many years ago, I taught a math class in the business department using Excel, and we created and analyzed data.
And business
created
math
charts,
or
graphs.
economics, I mean, those kinds of courses are perfect because we have released a lot of adults into the wild who do not understand the fundamentals. That's why they sign up for those high interest credit cards, right?
Yeah.
Okay? Who does that? People who don't understand number concepts. 19%, that doesn't sound so bad. 19 is kind of a lower number compared to 100. 19% is a little different than just 19. It's not $19, it's 19% of your dollars. That's a big difference. If you understood that interest rate, you would never sign up for that.
I feel like we have a huge upgrade battle with, we talked about credit acts a little earlier. Credit acts just first teacher there, and also students, they're so used to, just show me how to do it.
Yeah. Well, and that's why those 8 mathematical practices are so powerful. I think when we see a lot of conversations between high school districts and their feeder districts, that's where they're all starting, is let's get a common understanding of those 8 mathematical practices and have those conversations about, we are expecting kids to persevere, we are expecting kids to solve problems, we're expecting, we're not gonna get that if we don't, work through it. So, I agree. The other thing I wanted to spend some time talking to you about today were the 8 problem-solving structures. One of the things I gave you was a handout that actually shows from the standards. It's the table. That's it. I don't know that you're aware of this because it's really not referenced in the middle school and high school standards as much. And that table.
This one?
That one. There's 2 tables actually. Yeah. It's the one that's back to back. It's got it's got the additive structures on one side and the multiplicative structures on the back side. I've walked every grade level. I meet with my county by grade level. We meet kindergarten all together, first grade all together. I've walked every single one of those grade levels through this progression just to see how important their role is. And I've walked the middle school and the high school folks through it just so that they see what's going down to that level and what kindergartners are going to be able to do. And I find it fascinating that high school teachers are in awe of what kindergarten teachers are going to do sometimes. So I'm going to walk you through it a little bit because I think this is so pivotal for our algebra. I like this comment. Can you read it or? Now listen up. Nobody gets in here without answering the following question. A train leaves Philadelphia at 1 p.m. It's traveling at 65 miles per hour. Another train leaves Stanford at 4 o'clock. Say, you need some paper. A lot of people are here though, and when we talk about word problems and problem solving, the train problem always seems to come up, or the nightmares. I laugh because it's not simultaneous linear equations. We should be able to do this, right? But that's when we say to kids, when could you apply simultaneous linear equations? The train problem, right? It could be there. So here's what I want you to do first. Could you just make a problem? Make a word problem that is either a basic addition word problem or a basic multiplication, whatever. Just make a word problem. You can jot it down. You can just have it in your head. Everybody come up with one. Give me a thumbs up saying, okay, got one. I'm not writing it down, but I got one.
Just basic.
Basic, whatever you want. Okay, everybody's got one. Okay, so here's what I want you to consider. There are unknowns, okay? And even starting at the early grades, we think about where's the unknown. There are problems that have an initial unknown, like, I had some marbles. My mom gave me 4 more, and now I have 9. How many did I start with? There are change unknowns, like, I got here at 9 o'clock. I'm going to leave here at 12 o'clock. How long will I be here? Okay, I'm finding the elapsed time to change, right? There are final unknowns, like, there are,
Johnny has 2 apples, Mary has 3 apples. How many apples do they have all together?
was that your problem?
No.
Oh, but that's a final unknown. Thank you. I was trying to think of a complex one because the other ones were so simple, but that's fine. You get the idea, okay? Where's the unknown? Starting in kindergarten, students will work with change unknowns and final unknowns. They will not do initial unknowns or start unknowns. That happens starting first grade. Now that's got implications for Algebra 5 if I ever heard it, right? That idea of where's the unknown. They're going to be modeling with manipulatives and pictures and, like making tape diagrams and all that, with thinking about where's my unknown in both addition and subtraction, and then when they get to 3rd and 4th grade, they're going to start thinking about it with multiplication and division. And in 5th grade, they'll take all, they'll do it all. They're adding that on. 3rd grade can do multi-step problems, thinking about where's the unknown. I think that's rigorous. I think we have middle schoolers who don't know where the unknown is. I think we have high schoolers who don't know where the unknown is because they weren't taught about where's the unknown. Now let's think about the problem you made. Okay, where was the unknown? How many of us had an initial unknown problem in our head that we came up with? How many of us had a change unknown problem that we came up with? How many of us had a final unknown problem that we came up with? Do you know why that is? They are are the easiest. When we think about what we've been exposed to, textbooks are loaded with final unknowns, result unknowns. They have some change unknowns. They have very few start unknowns. We're exposed to it. They are expected to be able to solve them. Even we lean toward result unknowns. And we know they're supposed to be in all 3 locations. We're adults. We've got this. I mean, when I said it, you're all nodding your heads. We totally get it. What did we come up with? Result unknown. We do start with result unknown problems in kindergarten, and then we move to change unknowns. That's the expectation. And we want them to act it out with manipulatives and pictures. So that's one of the big ideas that's happening starting in, as I said, kindergarten with those 2. First grade does start unknowns. Part of the reason why we don't do start unknowns in kindergarten is because kindergarten solves problems through counting. And if they don't know where to start counting, they don't. So that's why they don't do start unknowns. They cannot start with an unknown. First graders, though, can. I have a big number line, and my daughter would, all this year, we would act out problems on it, where she'd like to step on the number line. So if I gave her start unknown problems, she would say, "You should have started the problem that way." She always yells at me like that. No, that's the point. But, it's fine. I take the abuse because she's thinking it through. Because she'll say, "Well, now I gotta work backwards and go back to the start, Mom." I know, I'm sorry. But that's the point, right? And I love when she exits on the number line and hops and everything. It's fun. Everybody should have a number line at their house, right?
Right.
Yes. Or in their classroom,
So we
right?
take the hopscotch and replace it with
Exactly. So here, if we think about, usually I put posters up around the room, but we're just gonna take a trip around the room mentally. Okay, I'm gonna walk you through this. So, the first problem-solving structure that we have is an adding 2 structure. Adding 2 is introduced in kindergarten, okay? Adding 2 sounds like this. I had 6 marbles. My mom gave me some more, and now I have 12. I don't know why I always start with marbles. I think I've lost many, but I always start with marbles. Okay, Zoobles. It's the Zoobles. Yes, Gabby's done it to me. Okay, so that's an adding 2 scenario. Where's the unknown?
The change.
The change. I rambled just to distract you, but you still caught on that it was a change unknown. Okay, adding 2 stories mean that you've got a quantity, we're adding to that quantity. They're very basic, okay? But the opposite of adding 2 is taking from. Also starts in K. We're gonna act it out with objects. I have 19 cupcakes and we eat 4, right? How many are left? Okay. I don't know why we started with a prime number. We just do because we have 19 cupcakes. Then we had extra batter. It's supposed to make 18 and I made a 19, right? Okay, taking from stories, interestingly, what do we call the answer to a subtraction problem?
The difference.
The difference. But when we're doing a taking from story, we're not actually finding the difference. We're finding how many are left or how many remain, which other countries in the world call that the remainder. We in this country decided in our infinite wisdom to simplify things and use only one term for the answer to a subtraction problem. Yet most subtraction stories that we tell with early learners are taking from stories where we're not finding the difference, although we call it that, we're finding the remainder. That's not confusing for kids, right? One of the things that I've been emphasizing with early educators is that they need to start introducing the word remainder for a remainder problem. Because when do we introduce the word remainder?
Division.
Division. And do kids see a connection between subtraction and division?
Nope.
But
Not
is
often.
there one?
Yes.
Yes. Do we think it might help if we introduce the word remainder when we were doing taking from stories? Absolutely. I find it fascinating that other countries of the world actually have the word remainder and they use it depending upon the context of the story. But we should do that, so we don't. So that's one of the shifts that we're trying to help them to make is if you're finding how many are left, call it the remainder. Maybe they'll connect it to division when they get to it in 3rd and 4th grade. Okay, so adding to, taking from, those are opposites. Then the next type we have are the putting together and taking apart, and those are really related. Sometimes it's hard to tell whether it's a putting together or a taking apart because it depends on how you want to think about it, and I don't think it matters. It's the part-whole relationship that we're trying to get at. But some people confuse putting together and adding to, where putting together might be, I have some marbles.